So device trees are the mechanism that's used for specifying the hardware. And so when we're working with a particular target platform, we have a BSP, a board support package for a board, and the device tree is the main part of that board support package. It allows us to describe the hardware. And so this is for the hardware which is what we could call non-discoverable. Some things, obviously, when we plug a USB key into our board, the kernel can discover that USB key. It doesn't need to have a device tree description. But for most of the static hardwired things on the board, we need that device tree description. And the device driver that drives the different pieces of hardware often needs to parse that description in order to pull out necessary information that it needs to be able to interact with that hardware. Now, in this presentation, we're primarily focusing on how the kernel can use the device tree. They can also be used by the bootloader and other parts of the process as well. So we can see just the diagram on the right-hand side here. We have the hardware. We have a device tree source that describes that hardware, which is compiled into what's called a device tree blob. And then the kernel and the kernel drivers will interact with that data, that blob, in memory. So if we focus initially at least on the ARM architecture, the old way, and it is very old now, it's been a long time since it was this way, to describe a board was to describe that board in C code, to have data structures in C files that would describe that hardware, and this would then be compiled into the kernel image. This was unwieldy, difficult to maintain, difficult to keep up to date, and so PowerPC and following that ARM and some other architecture families moved to use the device tree description. And what that means is that the bulk of our board support is within what's called the device tree, and then this is compiled into a separate binary object called the device tree blob, DTB, sometimes also called the flattened device tree or FDT, which is loaded by the bootloader typically alongside the kernel image when the target boots. The big advantage, or one of the big advantages of this approach, is that it allows us to separate the source of that device tree description. It doesn't have to come from within the kernel source tree. It can come from outside. It can come from another location. And it gives us a lot of flexibility then that we can change aspects of the description of the hardware without having to recompile our kernel image every single time. And if we look at this model, particularly if we're thinking about devices that have an FPGA, for example, where we need to describe the interface to that FPGA model in the device tree, that's only really possible to do that easily using this model where we have this separate board support device tree. If you are building device trees within the kernel source tree, then there is the kernel, the Linux kernel has its own make target, make DTBs, that will take, for example, here in Arch ARM boot DTS, so for the 32-bit ARM, will take whichever particular board you've configured your kernel to build, we'll pull in the source files, and we'll see these in more detail, and we'll output one or more DTBs, device tree blobs. If you're working with what we could call an out-of-tree device tree, a device tree which is defined just in source files somewhere else outside of the kernel source tree, then we can call what's called the device tree compiler directly, the DTC. Now this device tree compiler is called within the kernel source tree, and the kernel source tree in fact includes its own version of the DTC, but we can actually install, we can use that one, or we can install our own DTC, or you may get it with your cross toolchain or whatever. And actually using the DTC is very straightforward, as we can see here. At its simplest, it takes a DTS file, the top level DTS file, which as we'll see later may include others, other source files. We define what the input and output format is going to be, input DTS, output DTB, and then we use standard syntax minus lowercase o to provide the name of the output file. So if we run this command, we would get a device tree blob. one of the really useful aspects of the Devicetree compiler is that it actually works both ways. We can go forward to create Devicetree blobs, but we can also go backward. We can take a Devicetree blob and the Devicetree compiler can extract the data from that Devicetree blob and put it into a DTS file. You may lose the names of some of the structures within the data, but it should all be consistent, maybe using numeric identifiers. We saw in that slide how a top-level Devicetree source file, a DTS file, could include others, and that can be used in a very powerful way because we can actually augment or overwrite data by including subsequent Devicetree source files. Basically, at the first part of the compile stage, the DTC will concatenate all of the files together in the order in which they're defined. And so we can see in this example, we have node A that contains a property, but we also have node A and node A and the other two source files which are included. And we can see that a couple of these will add values and one will redefine a value, as we can see here, and we can see the results, the values that we'll get in the final Devicetree source. Notice also there's a couple of ways of including Devicetree source files, or DTS or DTSI, include files into Devicetree sources. There's one that uses the C preprocessor with a hash include, or there's the kind of Devicetree way of doing it with this syntax we can see on the top line there.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of Simon's webinar, Working with Device Trees, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.